Green steel is one of the most important industrial breakthroughs of our time. It promises to produce steel with a fraction of the carbon emissions of traditional methods. So why hasn't it replaced traditional steel? Every year, the world produces around 1.85 billion tons of steel. And in the process, it releases roughly 4 billion tons of carbon dioxide. That is precisely the problem green steel was designed to solve. So if green steel is the future, why does the old system still dominate? The answer is far more complicated than it first appears, because making green steel isn't just about reducing emissions. It's about replacing everything the existing system already provides. And that turns out to be far more difficult than anyone expected. So before we can understand green steel, we first need to understand how steel is made today. The direct reduced iron route and the blast furnace basic oxygen furnace route. Different technologies. The same beginning. Iron ore. Mined from the earth, crushed into smaller pieces, then upgraded. Preparing the ore for the route ahead. Depending on the route, some will become pellets, small, uniform spheres designed for modern steelmaking. Others will become sinter, produced by bonding fine iron ore into larger pieces. And some ore can be used directly as lump ore, but none of them are actually iron. Not yet, because the iron is still locked inside the ore, bound together with oxygen. And separating the two is the entire purpose of iron making. For more than a century, the blast furnace has been the dominant way of doing exactly that. It can use sinter, pellets, or lump ore, but iron ore alone isn't enough, because the blast furnace needs two more ingredients: limestone, helping remove impurities from the process, and most importantly, coke. It has to be manufactured, starting with coal. Inside massive coke ovens, coal is heated to extreme temperatures, not to burn it, but to transform it, driving off gases and impurities and leaving behind a carbon-rich material known as coke, a fuel specifically engineered for the blast furnace. And once it reaches the furnace, its job is only beginning. Inside the furnace, coke provides the intense heat needed to keep the process running. But its most important role is something else. removing the oxygen trapped inside the iron ore, releasing the iron needed to make steel. The result is molten iron, rich in carbon, but not yet steel. To become steel, it must pass through one more stage, the basic oxygen furnace, where excess carbon and impurities are removed. The result is steel, but it comes at a cost, because every step of this process depends on coke, and every ton of coke ultimately becomes carbon dioxide. And that's the problem. If coke is responsible for so much of the industry's emissions, what happens if we remove it? Can steel still be made? The answer is yes. This is the direct reduced iron route. The idea isn't new. The world's first commercial DRI plant began operating in 1957, long before the term green steel even existed. Instead of relying on coke inside a blast furnace, this process removes oxygen from iron ore without using coke at all. It begins inside the reformer. Before entering the shaft furnace, natural gas passes through the reformer, where it is converted into a hot reducing gas, rich in hydrogen and carbon monoxide. This hot gas then flows into the shaft furnace, while iron ore pellets are fed in from the top. As the pellets slowly descend, the reducing gas rises upward, pulling oxygen away from the ore, leaving behind nearly pure iron, known as direct reduced iron, or simply DRI. From there, the iron moves into an electric arc furnace, where electricity melts it into liquid steel, ready for casting and rolling. At first glance, it seems like the perfect solution. No blast furnace, no coke. But there is one important detail. The reducing gas still comes from natural gas, which means carbon dioxide is still being produced. So what if we remove the carbon from the reducing gas altogether? The answer is hydrogen. Instead of natural gas passing through a reformer, hydrogen is fed directly into the shaft furnace. The process remains almost the same, but instead of producing carbon dioxide, it produces water vapor. This is known as H2DRI. But solving one problem creates another. Using hydrogen doesn't automatically make steel green, because hydrogen doesn't simply exist on its own. It has to be produced first. Today, almost all of the world's hydrogen is still produced from fossil fuels. Around 3/4 comes from a process called steam methane reforming. Inside the reformer, natural gas reacts with steam, producing hydrogen, but also releasing large amounts of carbon dioxide, which means the emissions haven't disappeared. They've simply moved from the steel plant to the hydrogen plant. So where does green hydrogen come from? Instead of natural gas, it starts with water. Electricity splits water into hydrogen and oxygen. No carbon, no carbon dioxide. This is called green hydrogen. A single electrolyzer can produce around 23 kilograms of hydrogen every hour, but it consumes about 1.25 megawatts of electrical power to do it. Now imagine supplying not one machine, but hundreds of them, every day, to feed a single steel plant. Suddenly, the challenge is no longer making hydrogen. It's generating enough clean electricity to produce it at industrial scale. So where does all that clean electricity come from? Meeting that demand requires vast amounts of clean electricity, especially offshore wind farms, built offshore where strong winds blow more consistently. These giant turbines capture the energy of the wind, spinning generators to produce electricity. Working together, hundreds of them can generate gigawatts of clean power. Solar farms work differently. Rows of photovoltaic panels capture sunlight and convert it directly into electricity. Spread across vast areas, millions of panels work together to generate clean power throughout the day. Even with projects on this scale, producing enough clean electricity for the steel industry remains an enormous challenge. So, why hasn't green steel replaced traditional steel? The first reason is the blast furnace itself. It is one of the most optimized industrial systems ever built. Steel companies have invested billions of dollars into plants designed to operate continuously for decades. Replacing them cannot happen overnight. But the bigger challenge lies beyond the steel plant. To replace the world's 1.85 billion tons of steel production, green steel would require around 8,000 terawatt-hours of clean electricity every year, not mainly to power the steel mills, but to produce the hydrogen they depend on. That is the real bottleneck. The technology already exists. What we still lack is the clean energy system to support it. But that is beginning to change. Around the world, new offshore wind farms and solar projects are being built to supply vast amounts of clean electricity. Gigawatt-scale green hydrogen plants are now under development. New storage facilities, new transport networks, and new infrastructure designed to move hydrogen where it is needed. At the same time, many of today's new DRI plants are designed to operate with natural gas, but built ready to switch to hydrogen when it becomes available at industrial scale. The transition has already begun, not by replacing everything overnight, but by building the next generation of the steel industry, one step at a time. Perhaps the future of steel was never only about steel. It has always been about energy.